The first step for Bob when he sets up his RSA process is to find the two random numbers P and Q, each of approximately equal length and 150 up to maybe 300 digits long. Now, to find the random prime P, the first step is to choose a random integer of the appropriate size, and for this you need a good random number generator. Check if that's prime. If not, check the next number after that, and so on. Checking primality is something I haven't said much about before, but usually one, in fact always, one uses a probabilistic method. One does a sequence of tests, and with a rapidly decreasing error probability, one can be fairly certain that what one has is actually a prime. In fact, the probability of making an error would be equivalent to, say, or less than the probability of a hardware failure, or perhaps of having some sort of errant cosmic ray affecting the calculation. And similarly for Q. So there we multiply P and Q, and we end up with N equals PQ. So this is the most important number that Bob publishes. Another number he needs is the number P minus 1 times Q minus 1, for reasons we'll see in just a minute. So now we have P and Q, which are certainly not published. We have N, which is published, and M, which is certainly not published. One then chooses a prime number E, bigger than or equal to 3 and less than M, such that E does not divide M. So in particular, the greatest common divisor of E and M will equal 1. An alternative approach is to take the number E to equal this, 2 to the 16 plus 1, which is, as we mentioned, 65537. This is a prime, and then to make sure that in the process of choosing P and Q, E did not divide P minus 1 or Q minus 1. Because if that's the case, and since E is prime, that means that E does not divide M, being the product of P minus 1 and Q minus 1. And so, again, we have the greatest common divisor of E and M is equal to 1. The reason for this particular choice of E, apart from being prime, is that it makes the computations for the encryption part of RSA fairly easy, and moreover, it has the advantage that it's large enough that it compensates for the possibility of poor padding in short messages. So now, because of this condition here, by a previous result we had, there must be some number D between 1 and M, which when multiplied by E is equal to 1, or congruent to 1, modulo M. And we can find D fairly simply and quickly by using the extended Euclidean algorithm. So now we have the number N and the number E, and those two are the public key that Bob publishes. The number D, which remember was the inverse of E, modulo M, is kept secret. And in fact, it would probably be a good strategy for Bob at this point to destroy all his calculations, and in particular numbers like M, and certainly leave no track of P or Q. If Alice wishes to send Bob a secret message, the first point is that she should translate M into W by the process we mentioned before of simply replacing each letter or number or character in M by an appropriate number, two-digit number, and that gives us the number W. So now we have the secret number W. And by the padding and or splitting, we can assume that W is less than N and of length similar to N, say at least 2/3 the length of N. This is for security of the RSA encryption method. So now, using the published NE by Bob, Alice computes W to the power E, remember W is her secret number, W to the power E modulo N. And this is done by methods we discussed before. This is a very quick calculation. C, modular arithmetic, modular operations, exponentiation example. And then Alice publishes C. Bob is the only person who can actually decrypt C back into W and hence into M. And what Bob does is he uses his private key. He takes the number C, raises it to the power D, and works out the remainder modulo N by the process here. And then, by the RSA theorem, which we're going to prove a little later, W, in fact, is equal to D. That is the RSA theorem. And you then strip any junk from the beginning of W and convert the message back into M. And that's the end of the process. We'll go through two examples, a toy example and then essentially a real life example in future videos, and then we'll prove the RSA theorem after that.